of all, when you solve a logarithm, what are you solving?
An exponent.
An exponent, exactly right. So let's just say that we had some sort of problem. I'll use that 216 one. Let's say you had 2 to the x equals 16. This is a problem that's simple enough you can just solve it just by looking at it. You'd say 2 to the 1 is 16, and the answer is?
2 to the power 4.
Yeah, 2 to the power 4. And you can either look at the first page of that packet that we did last time, or you can just think in your head and say 2 times 2 is 4, times 2 is 8, times 2 is 16. So the answer is 4. Anytime x is in the exponent, you are technically solving a logarithm. Okay? Whether logarithms pop up or not, like right here, we just solved it by inspection. We just say, hey, 2 to the 4th is 16. Technically, what you just did there is a logarithmic process. So, how do you read log 216? What I just said was incorrect. How do you read log 216? How would you say that in proper English?
Log to the second. 16?
Well,
No.
2 times what equals, or 2 to the power
Well, you
4.
could reread it that way. Okay, there's a few ways. You could say, what'd you say? 2 to the
power of what equals.
You can say 2 to the 1 is 16. But how would you just read that? Like if you're going to talk to someone over the phone and you're like, okay, the problem is
Log base 2.
yeah, correct. Log base 2 of
Nice, good job.
16. So you'd say log base 2 of 16. And the keywords there are base and up. So that's log base 2 of 16. What you wouldn't want to say is log 216 because that's very confusing. Are you saying log 216? Because that's a very different problem. That would be implied base 10. And now all of a sudden you're solving something completely different. So in order for us to be able to communicate with each other, it's important that we all say log base 2 of 16. Keep in mind, of comes from function notation. Like if you had f of x, you hear the word of, equals x squared plus 3, and then I want to find f of 3. So of means that's the input. So this is f of 3 because 3 is the input. And here this is log base 2 of 16 because technically this is log base 2 parenthesis 16. And you're inputting 16 into the function called log base 2. So it's log base 2 of 16. And how do we read it as a question? I wrote it as an equation, but how do you read it as a question?
2 what?
Yeah, 2 to the what is 16. All right, so just take a look at that. That's 3 equivalent ways of talking about that one simple equation right there. Okay, now how do you convert 3 to the x into log form? So here I'm going to write this down in exponential form. So exponential form, we would have the equation 3 to the x equals 81. How do we rewrite that in log form?
Be log 3.
Log what?
Right.
Log what?
Base 3.
We have log base 3.
81.
Yeah, of 81.
Of 81 equals x.
Yeah, exactly right. Equals x. Okay, so now that's log form and that's exponential form. Exponential form is anything that has an exponent. Okay, so do you see an exponent in here? X has an exponent of 1. That doesn't really count. 81 has an exponent of 1. That doesn't really count. So no, this is not exponential form. This is log form because this is the word log. But exponential form because there's an exponent. Okay, so yeah, those are our exponential form and log form. One of the fundamental activities we do is simply switch back and forth between the two forms. So if somebody hands you an exponential equation, you convert it into log form. Somebody hands you a log form, you convert it into exponential form. That might seem backwards, like, why don't they just hand me what they want me to use, right? But no, almost always you're handed it in one way and then you have to switch it to solve it. Okay, anything else to say about that? I don't think so. So what is the base log? So on your calculator, what does the log button actually mean? LOG.
10. Or base 10.
Yeah, that's the log base 10. And by log base 10, what we're really saying is that we're solving an equation of the form 10 to the what equals n, where n is just some number, right? Furthermore, this is an exponential function, so it's an exponential graph. What does an exponential graph look like? Looks like that, right? And so over here to the left, we have an asymptote. Over here to the right, it just blasts off. I call it blast off like a rocket. And what you notice is that the value of the function is always where? It's always above the x-axis. And the asymptote will never touch down and land on the x-axis. So this thing is always greater than or equal to 0. So the n number is always positive. It's only a positive number that we can set it equal to. So what does that mean? Well, yeah, that's what that means so far. On your calculator, what is ln?
Log base E.
Yeah, that one is log base e, where e is that special number 2.71, 82, 81, 2, etc. And that means we're solving equations like e to the x equals a positive number. Once again, e to the x looks just like it. It's just an exponential graph with an asymptote to the left. Okay, folks, what else should we say about this? Does this sound familiar? This is what we talked about last time? Yeah, I think so. One other consideration, because of the fact that the graph is always above the x-axis, what do we know about a domain error for a logarithm? So let's review domain. Domain, we know that we cannot divide by 0, and we know that we cannot square root the negative. So can we log 0? No, we cannot. And what would that even mean anyway? Log base 10 of 0, if we said, well, what is that? That's equal to 0. I'm sorry, that's equal to x, some unknown. We don't know what that is, but it's equal to x. So that's left to the right equals middle. That means solve the equation 10 to the x equals 0. But will the graph ever touch down on 0? No. So that's undefined. So we would say log of 0 is undefined, just like dividing by 0 is undefined. So you can't log a 0. And on the other hand, what about log of a negative? Can you log a negative number? What calculator error does your calculator give you that? It's not just undefined, it's
Domain error.
all of these are domain errors. Type it into your calculator. What do you get? If you do log of a negative number, it's not just a domain error. It's not just undefined. Non-real answer, it's imaginary. So I want you all to notice here the similarity here. That if you divide, you can't divide by 0, you can't log 0. Either way, that's undefined. And you can't square root a negative, and you can't log a negative. Either way, that's imaginary. Not that it's really key that we know the difference between undefined and imaginary, but this, for instance, is not an imaginary number. 1 divided by 0 is not imaginary. Log of 0 is not imaginary. It's simply undefined. Whereas these, actually, the letter I will pop up. And my calculator actually won't do imaginary numbers, but if you have a TI-84 or a TI-85, it'll actually do an imaginary calculation for you.
Yeah, it's like a 1.364376354.
Yeah, with I in it. Okay, well, there we go, folks. So today is April 1st. We're going to continue on through Chapter 6 today and Wednesday. The next week, you'll take your test. Like I said, there's your practice test. The solutions are online. Oh, gee, I didn't come up with another joke for you because I've already told you both of those. You don't have a good joke you want to share? Provided it's clean, short.
Let me see.
Oh, gee, nice, fun joke.
I'm coming up with one.
Oh, you are? Oh, you're going one? Well, here's just a classic for you. Knock, knock, everybody. Knock, knock.
Who's there?
Interrupting cow. Moo. I think it's a cute one. Okay, so then, folks, where did we get last time? We finished all of the problems that you see right there, and we finished all the problems through 20, right? So we're on to number 21.
I got one question. How do you make a negative number positive?
How do you make a negative number positive?
He marries another negative number.
Oh, well, there you go. Because negative times negative is positive. Very good. Okay, so folks, take a look at number 21 here. It's asking for a domain. So we're going to approach these problems in 2 different ways. One is what we were just saying over here. Oh, and I forgot to write down the actual tests. The actual tests, if you recall, so here are our domain tests. Domain tests. So division by 0, you don't want the denominator to equal 0, so you'd write denominator not equal to 0. And you would solve that equation. If you don't want to square root a negative, you write radicand is greater than or equal to 0. And then you solve that equation using algebra. But if you want the log to be not negative and not 0, what does that mean? Like, look at a number line. I don't want it to be 0, and I don't want it to be negative. So what can I let it be? Yeah, any positive number. So what we're saying here now, and also some vocabulary for you. The number that you plug in as the input into a logarithm is called the argument. You don't just call it the input, you call it the argument. Now, I don't know why they call it the argument, but that's the vocabulary word that's used. So whatever number you're plugging into the log, since log is a function and you're inputting a number, you call it the argument. So in this case, what we want is the argument to be greater than 0. The argument of a logarithm has to be greater than 0. So notice that these three tests are all different. The denominator just can't be 0. The radicand can be 0 or positive, whereas the argument can only be positive. So this is our domain test for a logarithm. The argument has to be greater than 0. So let's keep that in mind now as we do 21. We want to know the domain of this function, natural log x squared plus 1. Now recall, when we do domain questions and you look at the graph directly, the domain is simply how far to the left do you go and how far to the right do you go. Okay, so recall that. Then when we do the domain of a graph, you just have to say how far to the right, how far to the left. So let's look at that. Here's my graph, ln x squared plus 1. And how far to the left does it go? How far to the right does it go?
Can you say infinite?
Yeah, infinity to the left, infinity to the right. Is there a point in the middle there?
Yes.
Looks like it. Let's just double check. Yeah, there's a point there. It looks like the whole graph is filled in from left to right, so the domain is negative infinity to infinity. Everybody, you can go ahead and write that down. By just looking at the graph, the domain is negative infinity. I'm going to leave it draw a picture here.
How do you bracket here?
Infinity always takes parentheses because you can't get there. A bracket means included.
Oh, yeah.
Okay, now the second test, okay, that's just the graphical test. So this is graphically. We can also do this algebraically, using the rule we just said, that a logarithm must take a positive number. So that means we're always going to set the argument greater than 0. So let's set the argument greater than 0. Now what does that mean? Okay, now keep in mind, first we looked at a logarithm graph. That was a logarithm graph, and we said how far it went left to right. Now we're looking at the argument itself, and we're saying it has to be greater than 0. What did that mean? If you set a function greater than 0, what part of the graph, where do you want the graph to be? Above the x-axis. So we're saying, when is this parabola above the x-axis? Right, so we're shifting our thinking completely. Here we looked at the logarithm graph itself, saying how far did it go left to right. Now we're just looking at the argument inside the logarithm, and we're saying when is it greater than 0, which means when is it above the x-axis. And if I look at that graph, that's a parabola that's been shifted up 1. That's this graph. When is that graph above the x-axis? When is it above the x-axis? Always. No, always. And so, again, we should get the same answer. The domain is negative infinity to infinity. We should get the same answer, which we did. We're saying when is the parabola above the x-axis? Always. So negative infinity to infinity. So notice that was two very different ways to consider the domain of this function. Now, what does this mean again? Domain is the set of all possible inputs. So what number can I input into this function? Anything at all. Yeah, any real number. Yeah, that's important, any real number. There are some imaginary numbers that you could not plug in. All right, so that's 21. Let's continue doing both approaches. Graphically, we look at the original function and say left to right, and then argumentatively, looking at the argument and saying when is it above the x-axis. Okay, so number 22. We have f of x equals log base 7 of 4x plus 8. So again, log base 7 is the type of function that you're looking at, and 4x plus 8 is the input. So log base 7 is the function, 4x plus 8 is the input, that argument. So graphically, let's just go ahead and graph that first. Now, your graphing calculators, your TI, your Desmos, they cannot distinguish between log base 7 and log base anything else. So we're just going to type in log base 10, that's the only thing the calculator knows, and just know that the graph is still representing what we want it to represent. I typed in base 10 instead of base 7, but that doesn't change the fact that we're looking for when the argument is greater than 0. So take a look at the graph.
You can't divide that?
Well, you could. That's a fair point. You could do that, but we haven't covered the change of base rule yet. Yeah. And the fact is, the domain will still be correct. Yeah. Okay, so folks, how far to the left, how far to the right does it go? Yeah, it doesn't touch -2. That's an asymptote. So it goes as far to the left as -2, not included, and it goes as far to the right as infinity. So go ahead and jot down our answer. And, you know, make a little graph too. There's -2. That's a vertical asymptote. And the graph goes up and then over. So our domain graphically is -2 to infinity. That's the graphical solution. You just straight up graph the function they gave you, look for left to right, and you write down the domain. So that's the old way that we've done it. But now, algebraically, we need to set the argument, and if you don't mind, I'm just going to write arg. Instead of argument, I'll just write arg, which is what pirates say. Arg. Okay, so we want the argument greater than 0, so that means 4x plus 8 must be greater than 0, which means if you subtract 8, you get 4x must be greater than -8. And if you divide out 4, so positive 4, and that means that x must be greater than -2. And if you graph that on a number line, there's -2, it's got to be greater than it. And what answer do we get? Same exact answer. Of course we should. We should always get the same answer. Whether you do the graphical approach or the algebraic approach, you should get the same answer. That's what?
Above the x-axis.
Oh, right, we didn't even do that approach. We just set the argument greater than 0. If you did want to say, when is 4x plus 8 greater than above the x-axis, you would graph it, and you would see that that line cuts through like this. And therefore, it's above the x-axis from -2 to 50. Now, folks, you know how sometimes a teacher will show you more than one way to do a problem? Like right here, I'm showing you the graphical approach of the original function. And I'm showing you the algebraic approach by setting the argument greater than 0. So you have a graphical approach, you have an algebraic approach. There's 2 approaches. And then the teacher would say something like, I'm showing you 2 ways so that you can find which way is more comfortable to you and you can choose one as your method. Or really what I'm saying is, which approach should you use? Both. Right? Because then you can check. If you get the same answer both ways, then you know that you're doing well. Well, if you get the same answer both ways, does that mean you're actually correct? You can still be wrong. You can still have done it wrong both times, right? But it at least gives you a feeling of greater confidence, like, hey, there's a really good chance that I'm right, right? Okay, so we'll continue doing both methods so you feel comfortable with both. 23, we have this function, log, which, since there's no number there, what base is it? Yeah, 10. And we'll actually do all 3 approaches in this one because it's just so interesting. So in case you're like writing it down and labeling it, so approach number 1, okay, is graph the original. And you're looking, the domain is left to right. Right? So let's graph the original. The original is log x squared plus 9x plus 18. There we go. So how far left to right? Whoa. What's happening here?
Wait, can you zoom in?
It's a graphing error. It's an asymptote. We can't, you know, it's attempting to do an asymptote and then the computer fails to show that.
I got kind of the same thing. After the x-axis, it's blank.
Yeah, it's just blank. Yeah. Okay, so how far to the left does it go? To infinity. How far to the right does it go? To infinity. But there's this gap here in the middle.
So it doesn't get between -5
and -6 and -3. Yeah, so there's nothing in between -6 and -3. So we can go ahead and write down our domain. I would draw a number line first, folks. I'd say, okay, we're going to the left of -6 to infinity. And we're going to the right of -3 to infinity. Which means my domain is -infinity to -6 union -3. Now, is the -6 and -3 parentheses or brackets? Yeah, parentheses because it's an asymptote. You don't ever actually get to -6. Does everybody see that? Yeah, we never actually reach -6. We get closer and closer, but we never get there. Okay, so that's the approach number one. Graph the original function, and your domain is simply how far you go left to right. Approach number two is the algebraic approach. Algebraic. And we simply set the argument greater than 0. By the way, early on I taught my daughter the joke, what is a pirate's favorite letter? And a pirate's favorite letter is R. Right? So now she's starting to read and she can recognize letters, and like, let's say we're reading a word like that. And I'm like, what letter is that? And she'll say, R. Right? And then I say, R. And she'll say, no, not R, just R. Like she distinguishes between the two. One is the punchline of a joke, and the other is a letter. Okay, so yeah, we're saying R greater than 0. So our argument is x squared plus 9x plus 8.
Got a smart kid.
Yeah, it's very funny that she distinguishes there. Okay, so algebraically, what we want to do here is find, factor, find the 2x intercepts. Oh, that's 18. And know when is the parabola what? Above or below the x-axis? Above. So here again, we're saying above the x-axis. Think about how tricky this is for a moment, okay? That in this graph, we're going left to right. In this graph, we're looking above the x-axis. That's a lot, to memorize and remember and to understand. This is very subtle stuff. You could see how easily a student could flip-flop these and look at this one and go left to right, and look at this one and go above the x-axis. So it's very subtle stuff here. Okay, so what do you multiply? How do you factor this? What do you multiply to get 18 and add to make 9? Yeah, 6 and 3. So x plus 6, x plus 3. And then we do the zero product rule, and we say either x is equal to negative 6 or x is equal to negative 3. That gives us a graph of the parabola. So my parabola is at negative 1, 2, 3, and 4, 5, 6. And my parabola is facing up. It's x squared, positive x squared, so there's my parabola. And when is the parabola above the x-axis? Yeah, over here and over here. Which you'll notice gives us the exact same answer. The parabola is above the x-axis to the left of negative 6 and to the right of negative 3. And therefore, the algebraic approach also gives us that the domain is negative infinity to negative 6 union negative 3. Now, we do all this work. Let's remind ourselves what on earth we just said. What are we saying? Domain is the set of all possible inputs. So I can take any number from this interval and I can plug it into the function, and my calculator will compute an answer. If I take a number between negative 6 and negative 3, my calculator is saying error. Right? That's always what we're saying when we calculate a domain problem. We're saying these are the numbers you can input and your calculator will give you an answer. These are the numbers that if you input, your calculator will give you an error message. Because sometimes, if you get an error message on your calculator, you think you did something wrong. But in fact, that could just be the function. That function doesn't take that input. So it doesn't mean you're doing anything wrong at all. It just means that that number is not an input of that function. How does everybody feel about this? So we've got one more. We're going to try the last one. Let's do the graphical approach first. It's going to be, ooh, look at that thing. X squared plus 9x plus 18 all over 4x minus 20. Oh, good. I can just put in 20. All right. So look at this thing. Now notice what I just graphed. This is the log graph itself. So are we looking left, right, or are we looking above the x-axis? Yeah, we're doing the graph itself, so we're looking left to right. So number 24, we're looking at log of x squared plus 9x plus 18 over 4x minus 20. And the graph has this strange upside down looking parabola thing between negative 6 and negative 3. And it also has a vertical asymptote over there at 5 that shoots off to the right. So in terms of our left-right solution, everybody just let me zoom in here real quick. Do you all agree the graph exists between negative 6 and negative 3? Mm-hmm. And then if we look over here, it exists to the right of 5? Mm-hmm. Okay, so that's our domain. Let's write it down. The domain is that it exists between -6 and -3, union 5 to infinity. I don't know about you folks, but I remember the first week of class. And in the first week of class, on the second day of class, we spent a long time talking about domain and writing all this stuff down in interval notation. And see, now here we are. I mean, hopefully, I hope that all of this feels a lot more fluent and that we're just writing these things down. And what I really just wrote down was allowable inputs. So these are all the numbers I can plug into that function, and my calculator will give me an answer. Yep. Okay, so that was the first approach, which is just graph the original. So the second approach is greater term. So the argument now is that whole thing. X squared plus 9x plus 18 over 4x minus 1.
So you multiply both sides?
Well, see, this is a rational expression. And a rational expression, remember, is going to have vertical asymptotes, x-intercepts, horizontal asymptotes, slant asymptotes. So there's a lot going on right here. We could go ahead and factor the top. And those would be our x-intercepts. And then we could pull out the 4 on bottom, and that would be our vertical asymptote. And we could look at the leading ratio, the ratio of the leading terms. And since the power on top is bigger than the power on the bottom, that means there's going to be a slant asymptote. Well, let's just go ahead and look at it. I mean, this is something that we did in a previous chapter. Let's go ahead and just graph that thing and see what we get. That's what the graph looks like. Now let's look. Is there a vertical asymptote at x equals 5? Yeah, that's from the denominator. Is there a slant asymptote? There does appear to be a slant asymptote. And the x-intercepts are indeed at -6 and -3, which is what we expected from the numerator. Like, take a look, folks. We expected x-intercepts at -6 and -3, and they are. But we expected a vertical asymptote at 5, which there is. Okay, so now the slant asymptote, if my memory serves me correctly, is 0.25 x plus 3.5, and there's our slant asymptote. Okay. All of this is not critical to do the problem. We just need to ask ourselves, when is the graph above the x-axis? So I'm going to turn off my vertical asymptote, my horizontal asymptote, or my slant asymptote, and let's just ask the question, when is it above the x-axis? So first of all, over here it's above. So what is that from? 5 to infinity? So 5 to infinity, it's above. And then right here, it actually did go above just briefly, between -6 and -3. So when is the graph above the axis? I'm just going to draw that part. Between -6 and 3, it jumped above. And to the right of 5, it was up here. Therefore, our domain is which is the same answer we got. So between these two approaches of finding the domain of a logarithmic function, which way do you prefer? Do you prefer to graph the original one and look left to right? Who likes that one? Graph the original, look left to right. Maybe anyone? Or do you prefer to just look at the argument and say, when is the argument above the axis? Anybody else? Okay, well, hey, it's totally fine. Either way you want to do it, you can do that on the test and you'd get the right answer. Of course, it's nice to be familiar with both. All right, questions about that section? I'm sure you'll have one of those on your test and it'll be on your homework on more. Okay. Folks, very briefly, we'll just look at this section and write down what the graph transformations are. They just want to know the graph transformations. You remember graph transformations. Let me give you an example using a parabola, because that's what we've done a lot of in the past. So recall, if f of x equals x squared is the parent function, which is just a standard parabola that starts at the origin, then we can do a variety of transformations on it by adding and subtracting numbers. So what happens if I add or subtract a number outside the function?
Or up and down.
That goes up and down. So remember, if I add a number outside, then it's up and down and it's the same as what you'd expect. So plus 5 would be up 5. And now if I add a subtract number on the inside, so like let's say I wrote minus 2, what kind of movement is that? Yeah, right and left. Only it's not the same as what you'd expect. Minus 2 really means you move to the right. So now this is going to be right and left, and this is the opposite of what you'd expect. And then finally, so this is outside the function, because the function is x squared. So outside the function is vertical motion, inside the function, inside the square, meaning that it happens to the x directly. That's right-left motion. So if I put a negative sign out front, that's outside, which means it affects the vertical motion. And what does a negative out front do? It just flips it upside down. So that would flip it upside down. Okay, so everybody remember graph transformations? Those are the main transformations we did. Well, so that's all they're asking for here. And we can literally just look at these. So like, if your original graph is 3dx, which is just an exponential graph, how does this one get moved? And let's just down 1. Thank you, Gabe. I'm going to start calling on people. Sorry. You're the consciousness of the group right now. Okay, so now, how about this one? This is just an exponential graph, but now I've subtracted 1 from x itself. So first of all, what motion are we doing? Up, down, or right, left, maybe? Yeah, right, left. And which way does it actually move, Olivia? Right or left? Since it's minus 1. Yep, to the right one. Okay, so that's it. So whatever the parent graph is, this graph is just shifted to the right one. That's it. Whatever this parent graph was, this one was just shifted down 1. And that's it. So how about up here? Now again, there's a graph. We're just looking at the graph of log raised to of x. And then we added 1 to x itself. So first of all, is that right, left, or up, down? Since we added the 1 inside the function to the x itself, is it going right, left?
You're adding 1 right.
Yeah, you're adding 1 to x itself, inside the function.
And I'll say 1 left.
Yeah, you're correct. It moves right, left, and you go left. Exactly right. Exactly left. Exactly correct. I said exactly right. Okay, now this one, you've got a log function, and then you're taking that log function and you're adding 1 outside of it. So Omar, what kind of movement is that? Yeah, it just goes up 1. Yeah. So we're just looking at graph transformations. Here, now this one's fancy. Let's write this one down as a group. Everybody write down number 7. Just find some space, write it down. This is g of x is log base 3. Sorry, negative log base 3 of x minus 2. So we have 2 things happening. So what's this thing that's happening? We're subtracting 2 from x itself. So what does that do, Olivia? Yes, Omar, that is correct. So that's going to go right to, whereas the negative sign up front, bad idea, it's going to flip it upside down.
Our group is high speed today.
You what?
Our group is high speed today.
Yeah, yeah. Which is great. Okay, so there, that's number 7.
Let's spin all the Red Bull.
Okay, so that's 7. Boy, Red Bull, I haven't had one of those in a decade. That sounds good.
Is it though?
Is it though? Well, no, it's probably not good for you, but it sounds interesting. Okay, now 8. Everybody write down 8, because this one's quite interesting. We're going to say we want what happened to the original graph if it's negative natural log of 8 minus x. Now, first of all, we probably all know what the negative out front means. You just flip it upside down. Flip upside down. Which, what?
Isn't it, sorry, the 8 under the x, right? Isn't that mean?
Right, so now look here. We don't normally write factors like this. We normally write x plus or minus a number. This is backwards. So how do we rewrite that? Yeah, negative x plus 8. However, we also know that anytime you have a negative on the leading term, you have to factor out the leading negative. So now there's going to be negative natural log of negative 1 times x minus 8. So now what this actually is we have the first negative, which since it's outside the function is an up-down flip. So that's flip up-down. And then this minus 8, that we can read directly. That shifts it right and left, but it's actually right 8. And now this one is a negative inside the function. So which way would it flip? It would be flipping right-left. Now, do we actually have a word in English for flipping something right-left? Like if you flip something upside down, we all know flip it upside down. Put it upside down. What do you call something when you flip it left or right? Yeah, you call it a mirror image, or perhaps you call it turning around, because this is an eraser. The fuzzy side is facing me. If you wanted me to flip this left right, that's physically impossible for me to do. I cannot flip it left right, right? I could turn it around, but that didn't actually flip it left right. I turned it around. So the only way to flip something left right is by in reality, how do we flip things right left? We actually can't. Just imagine if I was standing here in front of you and you were like, hey, flip that right side left for me. And all of a sudden, the paper was actually written backwards. That would be magic, right? So I cannot flip things right side left.
Oh, I can.
You can?
Yeah.
That's amazing. However, you can walk up to a mirror and then hold it in the mirror and then look, and it would be flipped right side left, right? So that's why in reality we don't talk much about flipping things right side left, because you can't physically do it, only by looking in a mirror. Which, by the way, is it ever weird to you that the person you see in the mirror is not the person everyone in the world sees? It's kind of weird sometimes to see my reflected face, because I'm like, oh, that's what I look like to other people. Because I'm so used to me in the mirror, which is actually backwards. Everyone in the world sees me correctly. I see myself backwards. You know what I'm talking about, buddy?
She's like, what?
Is it a fixed? Is that a reflection?
Is that the reflection
of your reflection?
Photos?
Well, if you look at yourself in a photo, that's the real you.
But if selfie, you like the flip.
I don't know. You have to check to see the English.
Yeah,
Like,
it flips.
Oh, yeah, it does flip.
wait, so you're saying when I look at a selfie? No, when I look at a selfie,
When you take a picture.
right is still on the right. So that's not me right there. That's the reflected me.
Yeah.
Yeah.
Yeah, whereas if it did flip, I don't know, does the camera do that for you? I don't think so. Because right now my right hand's on the right.
There are some cameras that actually do that.
Yeah, there is something that does that for you. But yeah, so that's who I see every day of my life, but that's not who you see. Like if you just, if you looked at that face and then looked at this face, you'd realize that what's right is on left and what's left is on right. It's super weird.
But technically, you don't see yourself either.
You what?
You don't see yourself either.
Yeah, you can't even see yourself anyway. You just see the reflection of yourself.
Well, then you see what you perceive yourself to be.
Yeah, exactly right. Omar. Exactly right. Okay, so then that -1 means to flip left side right. Left, right, which is physically impossible. Now, here's another mind boggler. I saw a TED video about this other day. Why is it that when you look in a mirror, it does flip it left, right? It does. But why doesn't it flip it up, down? I don't even know the answer. I didn't finish the TED video, so I don't know why.
Because we're not negative.
Because what?
We're not negative.
What do you mean we're not negative?
There's not negative on the side of us.
Hmm?
You know how you if there's negative on the side, it flips us up down. But I have a negative on the side of us, therefore we're not flipping up.
What's a negative? Are you joking? It's
Yeah.
like, what? Okay, so all these are just graph transformations. And so they work in the normal way. And that's all I really had to say about that. All right. So now let's talk about properties of logarithms. Yeah, very good. So everybody turn to this page. And what we're going to talk about right now is the concept of simplifying versus simply rewriting. Because oftentimes in mathematics, you simplify things, but other times you simply rewrite it. So let's talk about the distinction there. Simplify versus rewrite. So to simplify something, let's say I gave you the fraction, I don't know, 20/40. Right? So if you wanted to simplify it, that means to make the number smaller, easier to manage. That's just 1/2. Whereas if I wanted you to rewrite something, I could take 1/2 and rewrite it as 3/6, or as 10/20, or I can write it as 5xy's over 10xy's, right? So simplifying implies that you're making the numbers more manageable and easier to use, whereas rewriting, you have infinite flexibility to rewrite something in a manner in which is helpful to you. Okay, one other thought. Let's say that you take x squared minus 25. Well, we could rewrite that as x plus 5, x minus 5. Is that simplified? Or is it just rewritten? Yeah, it's just rewritten, right? And again, we have this flexibility to take an expression and rewrite it in any way we like. Now, let's say that I took both of these expressions. I've got both of these expressions now, and I said I want to solve them for 0, like set it equals 0. Well, which way is easier? Well, they're both pretty much the same, right? Here I can move the 25 over for x squared equals 25, and then I square root both sides, and I get x is equal to plus or minus 5. Whereas here, set it equals 0, by the 0 product rule, I either have this or this, so x equals 5 or x equals negative 5. I mean, was either of them really easier than the other? Not necessarily in this case. And yet, rewriting, okay, just the mere act of rewriting, allows for flexibility. Okay? And that's very different. Simplifying normally means easier, whereas rewriting means flexible. It means that you can approach a problem in more than one way. You can see the problem in more than one way. And that's very helpful. So what we're about to look at is a way to rewrite logarithmic expressions. And the hope is that by rewriting it in a new way, it could give you a different approach to a problem that could be easier. What we're doing is not simplifying, it's merely rewriting. So let's start by going through the rules. These are called log properties. Although a lot of people will also refer to them as log rules, which I always then jokingly move the S and I say, logs rule, which is obviously how all of you feel. Okay, so what are our log rules? The first one states that the log of a product, so if I have log of A times B, I can actually rewrite that as log A plus log B. Okay, that's pretty interesting. A lot is interesting about this. First, I didn't specify the base. So since I didn't specify the base, we all assume that this is really a base 10. The fact is this formula will work for any base. It could be base 2, base 3, base whatever, base t. So now let's just see if this works. Okay, that's the rule. Let's look at an example. Let's say that I had log of 10 times 10. Because this one we can do in our head. So first of all, 10 times 10 is 100. You don't have to write all this, just the example. What's log of 100? Remember that's base 10. So 10 to the what is 100? 2. Okay, so let's hold on to that. Over here, log of 10 times 10 is really log 10 plus log 10. So I split that product up into an addition problem. So now what's log base 10 of 10? 10 to the what is 10? 10 to the what is 10? 1. And so is 2 equal to 1 plus 1? Yes. So indeed, that's just a simple example to show you that it works. So that's our first log rule. You could say that in English by saying the log of a product is the sum of the logs. So multiplication turns into addition. That's weird. That's really weird. Because for instance, let's say that I gave you another rule that you're all familiar with, such as simplifying a square root. If I have the square root of 20, and I call that the square root of 4 times 5, that becomes the square root of 4 times the square root of 5. Okay, multiplication didn't turn into addition. Like if root 4 times 5 became root 4 plus root 5, I'd like to think that everybody would look sideways at that. Like, what? Why would multiplication turn into addition? Right, so that's not the case for this rule. Multiplication stays multiplication. And yet, in logarithms, the log of a product becomes the sum of the logs. It's very interesting. I don't know of too many of the rules like that. Yeah, I'd be hard pressed. Okay, next rule. That was multiplication turning into addition. Can anyone take a guess what the next one will be? This is multiplication turning into addition.
Division turning into subtraction.
Yeah, division turns into subtraction. So log of a quotient becomes the difference of the logs. The way I really like to think of this is that the log of the numerator divided by the denominator is log of the numerator minus log of the denominator. So it goes numerator minus denominator, or top divided by bottom, top minus bottom. So again, an example, we could say, what if I had log of 100 divided by 10? So 100 divided by 10 is simply 10. Log base 10 of 10 is 1. So 10 to the what is 10? Whereas over here I have log of 100 minus log of 10. And so log of 100, that's 10 to the what is 100? 10 to the what is 100? 2. And 10 to the what is 10? And sure enough, 1 equals 2 minus 1. So it does work. So that's our second rule. So multiplication becomes addition, division becomes subtraction. Yeah, powers.
So how would you solve number 6?
We'll get there. But you asked me a question, Victor. How would I solve it? With paper and pencil. Okay, the last one is a power. So this is called the product rule, that's called the quotient rule, this is called the power rule. Log of a to the power of f. This is called the power rule, so I should write that down. So this is the product rule, this is the quotient rule, and this is the power rule. Power rule for logarithms. So the way this works, and it's very cute, watch as I do this. The exponent n comes out, down, and in front of the logarithm. So log of a to the n becomes n times log of a. So the exponent becomes simply a number that's getting multiplied by the log. I want you to notice again how remarkable that rule is. What if I told you that instead of doing 2 to the power of 10, which is 2, 4, 8, 16, 32, 64, 1, 98, 2, 56, 5, 12, 1,024. What if I said instead of doing 2 to the 10, you could just bring the 10 out front and do 10 times 2? I mean, that's ridiculous. And yet that's exactly what this rule states. That you just take the exponent out front and you get the same result. Let's try it. If we had log of 10 squared, okay, so 10 squared is 100, 10 to the what is 100? 2. So this answer is 2. Over here, I can just bring the 2 out front. So 2 times log 10. And again, log 10, 10 to the 1 is 10. 1, 2 times 1 is 2. So the answer is 2 equals 2, and it works. Okay, so as we do these problems, what you do is you scan the problem, and you look for products, you look for quotients, you look for powers. And you just ask yourself, okay, do I see a product? Do I see a quotient? Do I see a power? And then you apply the rule as you see them. So those are our rules. Now let's go ahead and try them. Now what we're about to do is not simplifying. It's just rewriting it. It's just rewriting it using a rule. So we have log of 1,000 x cubed y to the 5th. Now, let's just run through the rules. Do we have a product?
Yeah.
We do. In fact, we have a triple product. We have 1,000 times x cubed times y to the 5th. So we do have things being multiplied. Do we have quotients? No fractions. Do we have a power? Yeah, we've got x cubed and y to the 5th. So right now, the question is, which rule do I do first? Do I bring the exponent out front, or do I break it up from multiplication into addition?
What kind of
It's kind of like PEMDAS.
so there's an order.
There is an order, but it's not exactly PEMDAS, because PEMDAS would say do exponents first. But right now, I can't bring the 3 out front, because the fact is that's an exponent of 1, that's an exponent of 3, and that's an exponent of 5. You can only bring an exponent out. Let's give a contrasting example. If it was log of 1,000 x cubed y to the 5th squared, now that whole thing is being raised to the power of 2. So I can bring the 2 out. But right now, this whole thing isn't being raised to a single exponent. So what I have to do first is break it apart.
You say that the opposite of it?
I don't think anything would be safe to say.
The opposite of PEMDAS, so
I tell you what you could do. You could look for the outermost structure. You're looking for the outermost structure. And right now, the outermost structure is the fact that I have 3 things being multiplied. We'll keep working on this. I know you want a rule. And really, the rule would be to scan through all 3 rules and see if you can apply it. You can only apply the power rule if the power is on the whole expression. Okay, so let's do the product first. It's 3 of them, so you just break it into log of 1,000 plus log of x cubed plus log of y to the 5th. So when you have a product, you just turn each product into addition. I know that was 3 of them instead of 2 of them, but it works the same way. Now, each of these in turn can be rewritten again. What is this one? This is log base 10 of 1,000 So 10 to the what is 1,000? Yeah, 3. Now, here we can actually apply the power rule. We have an exponent, it's on the entire expression, so the 3 can come out front, same thing with 5. So what do we have? We have 3 plus 3 log x plus 5 log y. And that's the answer. I say answer in quotation marks because all we did was rewrite it. This original expression is equal to the final expression. And so you just look at it and say, is that easier to use? The answer is probably. Because, you know, if you're looking at a big number, like let's say y is 982. Do you really want to raise 982 to the power of 5? It'd be a very, very big, unwieldy number. Whereas if I just have 982, I just make log of 982, then multiply times 5. And that's a whole lot easier than multiplying 982 times itself 5 times. Okay, that's number 1. Let's all try it. Number 2. And number 2, we have log base 5 of 0 to 25. So let's just scan through the rules. Do we have a product? No. Do we have a quotient? Yes. Do we have a power? Yeah. And the question asked for the power is the power on the whole thing? Yes, the power is on the whole thing. And so you can bring the power out. I think maybe that would be the good first step, is look for the power rule first, and if the power is on the whole thing, bring it out. So now what we have is 3. I'm going to put brackets, log base 5 of 0 to 25. So that's the first thing. Okay, do we have a product? No. Do we have a quotient? Yes, we have a quotient. So now watch again. I'm going to do 3 bracket, and we're going to turn division into subtraction. So that's going to be log base 5 of z minus log base 5 25. Okay, now what can we do? Nothing with the log base 5 of z. But what about log base 5 of 25? Yeah, 5 to the 1 is 25. That's 2. So now we have 3 log base 5 of z minus 2. And right here, you could either say you're done, or you could distribute into 3, and you might find that 3 log base 5 of z minus 6 looks a little better. Now, when you rewrite something, it's not often the case that any rewriting is better than any other rewrite. However, we can go ahead and say something about the problems that we've just seen. This original form we would call condensed, because it's condensed down into a single logarithm. Whereas this we would call expanded, because the argument is a single item. Now that's an interesting difference. Here, there's a single logarithm, and the argument is very complex. Here, there are multiple logarithms, but the argument is always just one thing. So that's kind of the difference. Do you want one logarithm with a complex argument, or do you want one argument with lots of logarithms? And that's the difference between expanded and condensed. Yep. What does everybody think about that? Now you can see how right now you might be saying, all right, like, what good is it? And the fact is we're still building up our logarithmic theory in order to solve real problems. So far we've just been learning definitions and definitions and definitions. They want to get in. They're out there trying to get in. They're like, I want to learn about logarithms. Okay, so let's try rewriting a couple more. This is all just practice for actually getting up to equations. So number 3. On number 3, we have natural log of root z over xy. Now, in mathematics, just like Batman has a utility belt with lots and lots of tools, I mean, just think of how useless Batman would be if he showed up without any utility belt and no tools. I mean, he's just got his fists of fury, and that's it. Like,
It's the same thing as saying, what's Tony Stark without his suit?
what?
What's Tony Stark without his suit?
What? Tony Stark?
Yeah, billionaire,
Iron Man.
playboy.
Yeah.
Iron Man.
Yeah, oh, Iron Man, yeah. So, see, you need a tool belt in mathematics to be able to do things. So, like, for instance, we need to know things like x to the a times x to the b is equal to x to the a plus b. And that's just something you're expected to know for the rest of your life. And x to the a over x to the b is x to the a minus b. And that's just something you're expected to know for the rest of your life. And x to the a to the power of b is x to the a times b. All these things are just in your tool bag. You're supposed to have them in the back of your mind at all times, thinking, can I apply that definition? Can I apply that definition? Can I apply that definition? And then we have things like root x is equal to x to the 1/2. You should just know that off the top of your head, ready to use it at any moment. Cube root of x is x to the 1/3. And nth root of x is x to the 1n. So knowing these things off the top of your head is critical for your ability as a mathematician. Much like Batman, he needs a utility belt, without which he's lost. So I look at this, and what's one random definition you could apply over here? What's some way in which we could rewrite this expression? Keeping in mind that we ultimately want to use a product rule, a quotient rule, and a power rule. Let's just look. Do we have a product? Yeah, x, y is a product. Do we have a quotient? Yeah, the division sign, the fraction. Do we have a power?
Yes.
Do we have a power?
Yes.
We do. The square root of x is a power. Sorry, the square root of z. So immediately, let's rewrite that as natural log of z to the 1/2 over xy. Because now we have a power, we have a product, and we have a quotient. And now the question becomes, which rule do we apply first? Which was what Gabe was asking, like, which one do you apply first? Well, first of all, the power is not being applied to the whole thing. So not the power. Yeah, the quotient is correct. The product is in the denominator only, so we can't do that yet. The overall structure of what we see here, the overall structure, like if you just zoomed out and let your eyes rest on it in a fuzzy way, you're looking at something divided by something. Like that's the overall structure that we're looking at. So the quotient rule is what we do first. So we would change that into the natural log of the numerator minus the natural log of the denominator. That would be step one. Now we can apply our power rule right here. So that's z to the 1/2. The 1/2 can come out front. So that's 1/2 natural log of z. Now this is natural log of a product. So we can change that product into addition. But notice there's a subtraction sign in front. So we need to do minus bracket and then rewrite the natural log of xy, which by the product rule is simply natural log of x plus natural log of y. And then we distribute the minus across the parentheses or brackets. So we have 1/2 natural log z minus natural log x minus natural log y. And what we have done is taken a single logarithm with a complex argument and turned it into many logarithms with a simple argument. One other thing that I want you all to see real quick, I'm going to put that 1/2 back up on the z because I can. You know, that's the power of rewriting. You can rewrite things any way you want, so long as you follow the rules. I want you to notice something. Does everyone agree that that first logarithm is positive? Okay, everyone watch really closely. When you have a log of a quotient, every term in the numerator becomes a positive log, and every term in the denominator becomes a negative log. So the square root of z is in the numerator, it's a positive log. The x is in the denominator, it's a negative log x. The y is in the denominator, it's a negative log y. You'll hear me saying log even though it's ln, because it's still just a log with bases.
No exceptions.
Right, no exceptions. So watch this, this is kind of fun. Let's say that I had log of AB over CD. I can just go ahead and immediately write down positive log A plus log B minus log C minus log D. You see what I did? Every term that was in the numerator is a positive log. Every term that was in the denominator is a negative log. And that's it. You can just split it apart like that. And then you aren't necessarily thinking about quotient product. You're just saying Numerator terms are positive logs, denominator terms are negative logs. It's a perfectly valid rule. It's just not normally the way they write it. Okay, I know my phone went off. Maybe that's as good as possible to stop this. Let's just stop right here and we'll take a break. 133, let's come back at 143.
Interesting fact. I'm from
Yeah.
Illinois.
Yeah.
I just found out they're going to tax people whenever.
They're going to tax people when it rains
Yeah.
in Illinois.
Yeah.
Right?
Why would you tax people? Why would you get taxed for when it rains?
Well, it makes sense to me. Rain can incur costs for the city. Like when it rains, there could be increased costs for cleaning the streets or sewage or who knows what, and so they need money to pay for it. And so instead of just universally taxing everybody at a higher rate and getting more money all the time, they just get money when there's a national emergency, which apparently is raining.
Yeah. I just find it strange that wherever it rains and it doesn't really destroy anything. Like,
Right. Yeah, it is strange. Don't get me wrong. I'm sorry. It is strange.
I would expect that more out of like Louisiana, honestly. 'Cause, like, nothing gets really destroyed
Mm-hmm.
up there. You originally from here?
Sorry, what?
You originally from here?
Dealing?
No, from Arizona.
Yeah, I'm from here.
I do my. When's your birthday?
November.
I like. I got like 4 years. What is your birthday?
Me? May 19th.
Are you in Taurus?
Where is it?
Yes. Ooh. I know.
She's on a roll, okay.
My
Mr. G,
boyfriend
what's
is
yours?
Tauro.
What's your birthday?
September
September what?
2nd.
Beautiful.
Okay. What?
I don't know.
Your
I
horoscope sign.
Oh, Virgo, yeah.
Yeah. I don't know myself.
So you know them all?
Yeah.
Which one is mine then? December 21st.
Capricorn.
Is it? I thought it was Sagittarius.
You know,
I think those two, the
My
sun
mom's
signs.
Sagittarius.
The
what
sun
day is
signs.
it? 20th?
14.
This is I'm on the age. I'm between.
Wait, isn't there like a little
14,
description of
14
of
well.
who someone is when
And
they're
she's
born
from-
on that kind of, on the month? During the,
Sagittarius starts from towards the end of November up to the 20th.
yeah, but doesn't someone
Or
like,
20, it's like
21st.
doesn't someone zodiac determine like a little bit of personality traits?
Some, I mean, they're not super accurate, but I just like to know.
Well, in the Chinese culture,
It's
they kind of
animals,
like,
like pig.
say we care about it. And they even have condoms.
They even
Their
have what?
condoms.
Okay.
With their,
Okay.
whatever horoscope is. Because they're like, it's like, if
Okay,
you're
wait,
a
wait,
Sagittarius,
okay.
you cannot be with a or if you are whatever, you cannot be with whoever.
Whoa. It's like
Oh,
here's the cock.
No, they're animals. Like the, like,
I'm a tiger.
Oh, well. Those-
I
you
give a
just-
rat.
they're- they're-
You
Yes.
just said they. For Chinese zodiacs,
Yes.
and I said, because one is a cock.
Oh my God. I'm thinking, I'm not thinking about it. I'm just that.
Is it compatible? Because
Yeah, compatibility.
compatibility, yeah.
Yeah, that's what.
I do not believe in that. Or who knows?
I don't know.
Do you believe in compatibility? Do you believe in compatibility?
Horoscope?
Yeah.
Like, what maybe.
Whoever.
All those compatibility things are 5%. The rest just depends on the person.
You?
Okay, so longest time here would be 5.
Yeah, that's awesome.
So what is you?
I'm just kidding. I'm gonna get used to the.
Yeah, I think.
All right, folks, let's do it. We have a couple more to expand, and then we will practice condensing. Now let's see. I don't know that we really need to do every single one of these examples together, because we've kind of seen the idea. But maybe what we can do now is apply this shortcut concept on the last two. Okay, well, let's start with number 4. Go back to the rules here. I showed you the rule for the log of a product, the log of a quotient, and the log of a power. Did we talk about the rule for a sum? Log of A plus B? We did not talk about that because there is no rule. You cannot rewrite it. If you have a log and a sum, don't rewrite it. It cannot be rewritten. Yeah, cannot be rewritten.
Is there gonna be a question?
Number 4.
No problem.
Oh, nah. I mean, I could just put a trick question on the test, but that one can't be rewritten. Did we go over the rule for a log of a difference?
Same thing.
Because it cannot be rewritten.
Oh, wait, so what about, because I'm not trying to note number 4 for myself, and I'm seeing x here, minus 5, it cannot be rewritten.
Well, it can be rewritten as it is. If you just leave it as x squared minus 25, you'd be stuck. There would be no way to rewrite it. However, you all know how to factor. So what is x squared minus 25 factored? That's a difference of 2 squares. So it could be,
X plus 5x minus 50.
exactly. And now that you've rewritten it, now it is a product. And now you can rewrite it as log of x plus 5 plus log of x minus 5. Now again, I just really want you all to see how important a tool belt is. A tool belt is so important because just knowing the difference of squares formula, the x squared minus a squared is x minus a times x plus a. What you're looking for in mathematics is always a way to move forward. You know, how can I move forward from here? And sometimes you don't even know about moving forward. You could be stepping laterally, right? Like, let's say that you're just in a dark room and you're trying to get somewhere and you're trying to move forward, then you hit a wall. Well, try to move forward anymore, you can't. But if you step sideways, maybe then you could keep moving forward. And this whole notion of rewriting is a way of taking lateral movement to think of the problem in a different way so that you can move forward. I'm not just talking about math problems right here, I'm talking about life, right? Rewriting an expression is lateral thinking, to reframe the problem in a new way of thinking so that you can still move forward. Now, to be honest, I mean, at this point, can we rewrite the log of the sum? Can you rewrite the log of the sum? No. Can you rewrite the log of difference? No. But we still got somewhere different than how we started. And sometimes that's all you need, is just a subtle shift in thinking so that you can move forward. Okay, number 5. So yeah, there wasn't much that we could do there.
If you don't have an exponent, you don't do
Right, there's no exponent. Yep. Number 5, we do have a quotient, and we're going to practice this idea of anything in the numerator is a positive log, anything in the denominator is a negative log. So try it with me. We're going to go right from the beginning to the end. So it's log base 3 of x squared over 81 minus 4. Now notice I put a multiplication dot between the 81 and the y minus 4. Because I wanted to call attention to the fact that that's a product. That's two separate things in the denominator. So here we go. Anything in the numerator is a positive log. Anything in the denominator is a negative log. So we can immediately rewrite this as positive log base 3x squared minus, because 81's at the bottom, minus log base 381, and minus, because y to the 4th is at the bottom, log base 3 y to the 4th. So how does that feel? Any term in the numerator becomes a positive log. Any term in the denominator becomes a negative log. Now, what can we do next? Again, think of our rules: product, quotient, power. So,
the powers.
yeah, we can now do the powers. Right? So that 2 can drop out front, 4 can drop out front, and log base 3 of 81. We can solve that in our head. 3 of the what is 81? So that's 3 times 3 is 9, times 3 is 27, times 3 is 81. So now what do we write? We write 2 log base 3 of x minus 4 log base 3 of y. I'm going to tell a joke because I can't help myself. It's not a joke, it's just an analogy, okay? So, in English, I can just write a sentence like, I ate the chicken. Right? It's just a simple sentence, I ate the chicken. Whereas, what can I do? In English, I got lots of flexibility to rewrite this. I can write the fowl. Thusly chewed. I did swallow. Right? It's ridiculous. Right? I mean, you know, in both cases, I ate some chicken. But the point is, I've got this freedom to rewrite it in different ways, and that's all we're doing in this, right? We're just rewriting it in different ways. I had this expression, log base 3 of x squared over 81 y to the 4th. I rewrote it like this. And at first glance, you might be wondering to yourself, how is that of any benefit to me? And at first glance, there's not really an answer, right? It's just a way of rewriting things. So, I think there's one more that we can do. Let's do number 6, because it's a good one. Do you think it'd be possible to take the sentence, I ate the chicken, and turn it into a full paragraph?
Yes.
Yeah.
Probably. That'd be kind of silly. But fun, right? Very fun. Okay, last one. Natural log, 4th root of xy over ez. Now notice, x, y, z are variables. What's e?
The variable into itself.
That's ln.
It's the number 2.7182, A1, A2. It's that special new number we've learned. Pi is 3.14, e is 2.71. So e is the number which is the base of this logarithm right here. So ln is really log base e. So this is a great example culminating this idea of rewriting an expression. So how do you rewrite an expression? You need to know definitions. These are all definitions right here. You also need to know tool belt facts. You know, just other tool belt facts. So like, what's one definition we could apply here?
Or cubic square root of whatever.
We could apply that the fourth root is really x to the 1/4. So the fourth root of something is really x to the 1/4. So that's one definition. Let's go ahead and do it. We're going to rewrite that as natural log of xy over ez all to the power of 1/4. Okay. Now what are we doing right now? We're groping blindly in the dark, people. We're just applying definitions. You know, we see something and we think, gosh, how can I rewrite that? Because I have log rules for product quotient power. I don't have a log rule for a root, but hey, come to think of it, a root is a power. So I'm going to rewrite it as a power, and now what can I do? I can apply the power rule. So now I can bring the 1/4 up. So now that's 1/4 natural log x, y over z. Now, when I say groping blindly in the dark, that might sound like a bad thing. Let me try to say that better. Try something, right? Just try something. Try anything. Apply any rule you can think of and see where it goes. Okay, now, to here, we can go ahead and do the quotient rule and the product rule simultaneously because anything on the top is a positive log, anything on the bottom is a negative log. So the 1/4 stays out front with brackets, and then we can write down numerator terms first, natural log x plus natural log y, then denominator terms minus natural log e minus natural log z. Now notice we've already accomplished the goal of expansion. We expanded. We had a single log with a complex argument. Now every log I have has a single argument. Okay, well there's one more thing we can do. What's one more definition we can apply? Yeah, because e is a number. And natural log is really log base e. So now watch. We have 1/4 natural log x plus natural log y. I'm going to change the order. Minus natural log z minus log base e of e. Now what is log base e of e? Don't answer just yet. Let's say you're walking down the street and you saw log base e of e. And you say to yourself, what is that? Well, of course you can just take out your calculator and type in natural log of e. But if you didn't know what natural log of e was, who remembers the mathematical strategy we use? If you don't know what something is, you make it equal to x. You just turn it into a statement. Like right here, log base e of e is just pure ignorance. I don't know. But I call it something, and I call it knowledge, right? So now I have this. So now what do? This is a log form.
So put in the exponential.
Switch it to exponential form. Left to the right equals middle. E to the x equals e.
So it's 1.
And what exponents right here? 1. And since the bases are the same, the exponents are the same, and therefore x equals 1, and therefore log base e of e equals 1, which means natural log of e equals 1. So that was quite the chain of knowledge to figure that out, but now I know the natural log of e is just 1. So now I have 1/4, and then the bracket, natural log x plus natural log y minus natural log z minus 1.
Would it not be 1/4?
Only if I distributed the 1/4.
Oh.
And you can. Omar, if you want to distribute the 1/4, it'd be 1/4 natural log x plus 1/4 natural log y minus 1/4 natural log z minus 1/4. That's totally up to you if you want to distribute the 1/4 or not. I think it's a little more clean to only have a single 1/4 at the beginning. And again, in the rules of, or in the game of rewriting, you can do anything you want. The question is, did the way you rewrite it help you get to an answer? Okay, so we've had, I think, a really nice philosophical discussion here about the difference between rewriting and simplifying. And then in order to be good at rewriting, you need to have a big tool belt, which means you need to have all these kind of rules in the back of your mind that you're thinking about and asking, hey, you know, when can I apply that rule? Can I apply that rule? And sometimes you apply a rule and it takes you nowhere. Like I've worked on problems where I'm like, okay, I'm gonna try it this way. I do a full page of work, I get nowhere. And I scrap it. That way didn't work. So you go back to the beginning. You try a different way. Okay. So now, if that was called expanding, let's try condensing. I think you'll like condensing. I'll leave all the rules up there. I think you'll like condensing a lot, actually. Because perhaps it's a little easier. Log base 2 of x plus log base 2 of y minus log base 2 of c. We can just write a single equals log base 2. Because now remember our goal. Now we're going to switch it around and condense. That means instead of lots of logs with single arguments, we're going to have one log with a complex argument. So what's our rule? Where does every positive log go to? Yeah, right up in the numerator. So far that's x, y up there. And where does any negative log go?
That's so 7 over xy, I mean 7 under xy.
I don't know what you're talking about. No, sir. Go ahead, Nick. I see it too.
I just said.
Oh, number 7. Yeah, number 7 is x, y over z. Yep, and that's it. How does everyone feel about that? Good. Yeah, isn't condensing better?
No, no.
Yeah. A little better. Number 8. Now, at number 8, there's something we have to do before we can condense. Who wants to say what we have to do before we can condense? What do we have to do?
Is it the 1/2? Do we have to put it back in? Or-
Yeah, you have to put the numbers in front back onto the exponent location. Because we're now putting everything inside the log. That's what we're trying to do. We're trying to put everything into one log. So we'll have to rewrite this one. So, and now furthermore, do I write x to the 1/2? Or what did I write? If that's x to the 1/2, that's really
X squared or x cubed. No. X.
You're getting there, Hector. I know you are. You wanted to say
X. Or root of x.
that's true. Okay, and then the next one is sure log y squared.
It's like calling
Minus x.
What is it? Calling kids. Do adventure kids over.
Now again, notice any positive log goes in the numerator, any negative log goes in the denominator. So we have a single log, which they didn't tell us the base. Oh, they did, 3. No, it's a 2. That's 3. Oh, I didn't even write it down. Shame on me. Does it matter that I didn't write it down?
Yeah.
Because there were no numbers involved, so I wasn't going to simplify it to the power of 3. But in any case, now we have the root x in the top, and we have y squared x in the bottom. This next one's really exciting. Now I know what you're thinking for number 9. I'll just throw those fractions up on the exponent, and then away you go. And maybe that's the case, but let's look. So we have, I'm going to go ahead and put the number in front on the exponent right now. So log x minus log z to the 1/3, and then plus log y to the 1/3. Well, actually, I guess there's nothing inside. So what's this one, positive or negative? Positive, positive. It doesn't hurt to write it, does it? Makes it more concrete, makes it more obvious to your brain. Positives go in the numerator, negatives go in the denominator. So we've got just one log. There's no base. Log. So up top I have an x. Up top I have a y to the 1/2, which is really root y. And at the bottom I have a z to the 1/3, which is really root 3. Is this feeling better? Because I mean, when we just started this half an hour ago, it probably felt like some alien language. Whereas now, just by doing it for a while, maybe now it's starting to feel good. Did I already tell you all my sister's avocado quote?
Please do.
Oh, it's brilliant. It's brilliant. Just wait for it. She said, when you first try avocado, it really doesn't taste like anything.
Oh, yeah.
But after a while, it tastes like avocado. Have I told you that one? I did, yeah. I mean, it's kind of like this. Like at first you're like, what? And then after a while, you're like, oh yeah, you do this.
I used that earlier too.
You what?
I used that earlier too.
Did you somewhere? Oh, that's fun. I'll tell my sister. Okay, now number 10, this will take some real lateral thinking. Log base what? Log base 5 of x minus 3. Now, we don't have a rule for a log minus a number, but we do have a rule for a log minus a log. Notice that if we had a log minus a log, we can compress it, condense it into a log of a quotient. But that second number isn't a log. Is there a way for me to rewrite that 3 so that I can rewrite it as log base 5 of something? Log base 5 of what would equal 3? 5 to the, we're asking, we want this, okay, to equal 3. No. Let's just look at this expression here real quick. I'm going to put something there. This is log base 5 half a base. And what do we want that to equal? 3. I've got an equation now. So this is left to the right equals middle. 5 to the 3 equals? What's 5 to the 3?
125.
5 times 5 is 25, and 25 times 5 is 125. And therefore, what number do I want there? Okay, now look at it, see if you agree. Is log base 5 and 125 equal to 3? Yeah. So there we have it. We have, instead of 3, we have log base 5 and 125.
I was going to say 124.
Close. Okay, so now I do have a difference, and I can run this formula backwards. If you do log minus a log, then it's log of numerator over denominator. Again, any positive term goes in the numerator, any negative term goes in the denominator. So what does this become?
X over.
Now this step was surprising. Like, I mean, really just now think about it. I can take any number I want. I'm going to take the number 3. And I could make that log base 2 of 8. I can make that log base 3 of 27. I can make that log base 4 of 64. I can make it log base 5 of 125. I can make it log base 6 of 216. You see what I'm doing? 2 cubed is 8, 3 cubed is 27, 4 to the third is 64, 5 cubed is 125, 6 cubed is 216. All of those equal 3. So that's an enormous flexibility, just like you can write 3 as 3 over 1, or 6 over 2, or 12 over 4. And what do you call all of this? Rewriting. To what end? Who knows? You're just rewriting it to see if it's helpful. Okay. Let's try, everybody try that yourself for number 11. Try to rewrite number 11. Change that number 2 into a log. And all of you could start, at least, by writing minus log base 7 something. Right? Because you want to rewrite the number 2 as a log base 7 of something. Notice again that you can apply a strategy that says, I want this to equal this. Everybody watch what I'm about to do, it's really funny. I want this to equal this. I want this to equal this. Right? So what is that? Again, as a log form, I just rewrite it. Left to the right equals middle. 7 squared equals, I don't know. And therefore, 49. So I put it at 49. And then when you're done, you look and you say, well, is that correct? 7 to the what is 49? So now that, oh, sorry, maybe I should have erased that already. Yeah, because I was saying, I want log base 7 of something, 2. Okay, so now that you've all done that, can we rewrite that as one log? Yeah. Remember, positive terms in the numerator, negative terms in the denominator. It's a positive log, so that term, that whole thing, x minus 3, that whole thing would go on top. X minus 3 as a factor. And the whole would go as a, yeah, you put parentheses, x minus 3 parentheses. Oh. Yeah, just like you would if like any other factor.
Do we know what the positive thing is though? Positive. Alright. Or a negative, or it's negative equal. So we have one base 7 actually. Plus 1 base 7. Okay. Don't put this with this. This.
Folks, I have one more recommendation for you. Because this last one is a little tricky because that x minus 3 thing. But what we know for sure is that any positive log goes up top, positive log goes up top, and a negative log goes on bottom. So you can start by just writing an empty structure. You've got 3 logs, you've got one item going on the top, another item going on the top, another item going on the bottom. And now it's just a matter of taking those items one at a time and plugging them in. Omar, did that make sense? Yeah. So that would be what you end up with.
If the bases are different, can you add them together? No, just multiply them?
You talking about the last one? Yeah. Yeah, I wonder what to do there.
This.
What? No, I'm trying to think, how do you approach something when you don't know what to do? You have a common base. Yeah, we want to do something there for sure. It's a good problem. Of course, Hector, how do I define
base
this
of
problem?
4 is 2.
What, Hector?
Common base of 4 is 2, so maybe 3, what goes in log 2 is the base of 2.
Which one?
I tried to break down the 4 into 2 separate ones. So since make them all bigger.
Yeah, well, let's look. So folks, the very last one, log base 2 of x plus log base 4 of x. Is that the problem? This problem is really exciting because when you first look at it, you have no idea what to do. You're like, this doesn't fit anything I know. And that's exciting. So what can we do?
Try something.
Let's try something. Let's try looking at each of these separately. All right, so like what's log base 2 of x? I don't know what it is. I'm going to call it y. And that really means 2 to the y equals x. I know that. And then over here, I have log base 4 of x. Well, what is that? I don't know either, but I'm going to call it z. So now I have 4 to the z equals x. Okay, so I've got something completely different now to look at. How could I rewrite this base so that they're the same base? Like, how do I rewrite 4 as a base of 2? 4 is really 2 squared. So now I have this original equation, and over here I have 2 to the 2z equals x. Because that's one of my toolkits, is that if I have an exponent to an exponent, I can multiply them. And so now what I really have is, instead of 4 to the z, I have 2 to the 2z. So now this one I can rewrite as log base 2 of x equals 2z. Now, you guys have to bet. We're just playing around with it. Like we're just rewriting things to see what we can get to. And what I have gotten to now is that this part right here My log base 4 of x was equal to z. Now I have 2z. If I divide off the 2, or better yet, multiply by 1/2, now I see that z is also equal to 1/2 of log base 2 of x, which means that log base 4 of x is also equal to 1/2 log base 2 of x. And so now I see that I can rewrite log base 4x as 1/2 log base 2x. I think I know I just went through that way too fast, and I know Valeria, you came in halfway through that problem. So first of all, I'm definitely not going to give a problem like this on the test, because I think it's a really solid, crazy question. But what we just found out is that if you had this, first of all, they're different bases, so you can't add them yet. But I did just find out that log base 4 of x is 1/2 log base 2 of x. So now I can change it into log base 2 of x plus 1/2 log base 2 of x. And now I do have the same base, so I push that 1/2 onto the top, so that's log base 2 of x plus log base 2 of x to the 1/2. Now they are the same base, so that'd be log base 2 of x times x to the 1/2. And what's that? What's x to the first times x to the 1/2?
Adam,
So that would be log base 2 of x to the 3s. Okay. In any case, folks, please, you can scratch out that problem. You can just scratch out that problem. In the entire time that I've ever taught this class, I've never seen a problem where they change the base. Not to say that it's not an interesting problem, but it won't be on your test. Okay. Folks, I think we are done with learning rules. Rewriting them. Well, to be fair, we have one more rule called the change of base rule. And then we're able to get on to just solving equations, because that's really what we want to do always. We want to solve equations. So we have one last rule here. It's a really nice one. They write it up in the gray box. I'm going to go ahead and write it down for you. And can we just follow the way they did it? Yep. I really don't like the way they did it. So let's say, here's the change of base rule. I'm going to write it down. Change of base. Now, keep in mind, we've been talking about logarithms like this. We said that if you have the exponential form, it's, no, it's not what we said. We said base to an exponent equals an answer, right? And then we rewrote that as log base b of a equals the exponent. There. So I think it's natural to have the base be the letter b, because that's the base. And I think it's natural to have that as letter a, because ultimately that's the answer that you're looking for. So everybody take log base b of a. And the motivation here is that your calculator only has a log base 10 button. So you can type that in. And your calculator only has log base e button. So you can type that in. Well, what if you came across an expression like log base 7 of 3? Your calculator can't do that. So that's our motivation. Our calculator only knows base 10 and base e. So what do you do if you get to log base 7? Your calculator can't do it. But the fact is, log base b of a can be rewritten as log a divided by log b, where both of those are base 10. And so your calculator can do it. To be fair, it's also natural log a divided by natural log b. So you can take any logarithm that's not a base 10 or a base e, and you can change it to be log of a divided by log b, or natural log of a divided by natural log b. Here's an example for you. We'll just do the example of the log base 7 of 3. Calculator doesn't know base 7. However, that will be equal to log of the big number divided by log of the little number. And both of those are your calculator log buttons. Okay, those are the calculator log base 10 buttons. Or you can type in natural log 3 divided by natural log 7. And I'd like you all to try it. So first of all, just to note how fun this is, we're saying 7 to the what is equal to 3. So wait, watch before you do your calculator. Watch me sandwich this. I'm saying 7 to what power will equal 3? Well, I know 7 to the 0 is equal to 1, and 7 to the 1 is equal to 7. So what must the answer be? The in between 0 and 1, right? So maybe x is 0.5, maybe 0.4, 0.3.
Or maybe it's 0.564.
Yeah, exactly. So now everyone go ahead and do parentheses now. You have to type parentheses log 3 divide by parentheses log 7. Go ahead. Yeah, 0.56 what?
457.
Okay, great. Okay, now that was, we did log 3 divided by log 7. Go ahead and do natural log 3 divided by natural log 7. Again, use parentheses, what do you get? Did you get exactly? Did you get the exact same answer? Exact same answer. So you remember now that I have said over and over again that your calculator does not have a log base 7 button, and it does not. But you can calculate log base 7 by simply dividing, okay, the big number divided by the little number. I'm saying big because it's large font, and little because it's the teeny tiny number down low. So it almost looks like a fraction already, doesn't it? So it's the 3 over the 7, log 3 over log 7. That's called the change of base rule, folks. This is a great rule, and I want us to be thoroughly impressed by it. So let's start by doing number 3. I will allow us to make a guess first. Log base 3 of 12. Okay, let's make a guess using the sandwich technique. So I want 3 to the what equals 12. If I did 3 squared, it would be 9. If I did 3 cubed, it would be 27. So what's your guess? Maybe 2.3? Did you already do it?
No, I
Oh, okay. So everybody now calculate log base 3 of 12. And again, on your calculator, I really think you need parentheses, because if I just type log 12 divided by log 3. You do? Oh, that makes me really sad. Nope, mine didn't. Yeah, parenthesis log 12 divided by parenthesis log 3. Yeah, I definitely need parentheses on mine. If you're using a TI, you need parentheses. Apparently, Omar doesn't need parentheses. But don't do what Omar does if you have a TI. Like Omar can do it because he has a Casio. But the rest of us with TIs, I don't know about you, Emily. What's yours?
Huh?
TI? Yeah.
Yeah.
Would you say the Casio is superior to the TI?
The Casio, you input information differently than a TI. I'm sure some features like this, the Casio is better. Other features, the TI would be better.
So the top one's what?
The key thing is that you closed the parenthesis around the argument.
Okay.
Yeah, well, either way. So Gabe pointed out something interesting. You can either type it as log 12 over log 3 with both parentheses. Notice there's parenthesis around the numerator and a parenthesis around the argument, parenthesis around the argument and a parenthesis around the denominator, or you can simply type log parenthesis of the argument divided by log parenthesis of the argument. Both of those will come out correct. What won't be correct is if your calculator automatically does a parenthesis, which is a 12, and then you type divide by log 3, and you type that. That's wrong. Because your calculator, when you hit the log button, it automatically gives you log parenthesis. See, your calculator is so smart, it knows you need parentheses. And so it just gives you a parenthesis.
It starts the argument for
Yeah. All right, so there we go. That's log base 3 of 12. Either way, you should have gotten the 2.26. So how about number 4? Now again, folks, number 4 is log base 5 of 80. You could go ahead and calculate this using the sandwich technique in your own head. Because you can say, well, let's see. That means I want to solve 5 to the what is 80. And I know 5 squared is 25. And I know 5 cubed is 125. So if you were standing around at a party with a bunch of other people, bumping elbows, talking math, and someone was like, what's log base 5 of 80? You'd be like, 2 something. Just say it all casual, be like, log base 5 of 80? You mean 2 something? Yeah, exactly. You just kind of round it. Okay, but anyway, so now that we've approximated, you can go ahead and do log 80 divided by log 5. And did everyone get 2.72? 27? Sorry, I should write it. So the change of base rule is log 80 divided by log 5. Anyway, that's the change of base rule. There's really not much else to say about it. Number 5 and number 6 are just making sure you know that it works with fractions and decimals as well. So like number 5 says log base 4 of 10. So that'd be log of 10 divided by log of 4. And it's still gonna work. And number 6, they're saying it'll work even if the base is a fraction. So log base 3/5 of 1,000 is log 1,000 over log 3/5. Or if you want to be wild, you can call it 0.6. X 3/5 is 0.6. Doesn't matter if you type it as a fraction or decimal. So that's the change of base rule. Okay. I feel like we should all take a nice big breath. Inhale, exhale about 10 times because we're about to transition from learning rules and definitions to solving equations. Right? So everything that we just did was to develop a toolbox of definitions and tools and rewritings so that we could just start solving equations. Because that's always what we want. We want to be able to solve an equation. That is, find the value of x that you can plug in to make the equation true. So, what's that, Melania? Okay. So, is everybody ready? We're going to solve some equations. Very excited. I mean, this is really what we build up to. So, why is this helpful? Solve the equation 2 to the x equals 10. Now recall, we have tried to solve a problem like this by the sandwich technique. We said 2 to the x is 10, so 2 cubed is 8, and 2 to the 4th is 16. And then we would start to do our sandwich, and we'd say, well, it's 2 to the 3.4 maybe. And you would do the sandwich technique until you got as many decimals of accuracy as you needed. But now look, 2 to the x equals 10. This is written in exponential form, so convert to log form. The first number stays the same, log base 2 of 10 equals x. So we're about to solve for x. Log base 2 of 10, your calculator doesn't know base 2, but it knows the change of base rule, and so it's log 10 over log 2. And that is x, and your calculator can do it. So this is very exciting. Here we go. Log 10 divided by log 2, and the answer is 3.321928095 ... How many decimals in that answer? Infinitely many. So there's our answer for x. And if you wanted to, you could turn around and check your answer. Because remember, always when you do algebra, you get an answer. How do you know if it's correct? You plug it back in and see if it makes a true sentence. So now I type 2 to the power of 3.321928095, and I get 10. It actually does 10 exactly. Now, obviously, that's not the end of the answer. There are more decimals, but my calculator, due to rounding error, gave me the right answer. So, folks, I'd say that's not too bad. A day and a half of building theories and definitions and properties so that we can now start solving equations. So here we go. Let's turn the page. We still have a whole other day. That's right. We still have a whole other day. That's wonderful. Boy, I wish we had more days. Vlogs are so fun and interesting. I don't think I can reschedule it. All right. It says, let's now read this gray box. Steps for solving an equation involving exponential functions. First, isolate the exponential function. And then, if convenient, express both sides with a common base and equate the exponents. Or take the log of both sides and use the power rule. Okay, we'll look at both of those. So let's take a look at number 1. 2 to the 4x equals 8. Now, one thing we already said you could do is rewrite both bases to be the same number. And at this point, you should recognize the number 8 as a power of 2. And you would say, hey, this is 2 to the 4x equals 2 to the 3. And then you would say, hey, I've got the same base on both sides. Therefore, the exponents must be equal. So by the sheer force of logic, 4x is equal to 3, and so x is equal to 0.75. That's one approach. And that approach, if you want to write it down, is called equate the bases, equate the exponents. And do you see that's what we did? First, we equated the bases. That is, you had to do the work to make both bases be the same numbers. And then you equate the exponents by just setting them equal to each other and you solve. Let's try that technique one more time. And number 2. So number 2, we have 5, 2x minus 1 equals 125. And again, at this point, I would say you should be looking at the number 125 and saying, hey, I recognize 125. That's 5 to the power of 3, 5 cubed. So we equate the bases. So you'll notice that was one kind of work that you did. You had to think about the number 125 and think, how do I rewrite that as a power of 5? And then you had to go figure it out. But now that we have equated the bases, we can equate the exponents. So now we say 2x minus 1 must be equal to 3. That's how you just do algebra. You'll notice this is just algebra now. There's no more exponentials, there's no logarithm, it's just algebra, so I have the 1 over, I get 2x equals 4, divide the 2 over, and x equals 2.
Is the final answer x equals?
What?
That's the final.
That's the final answer.
Okay, so you don't rewrite the.
No, you don't have to go back to exponential form. The answer is just x equals 2.
Okay.
How do we know the answer is x equals 2? Yeah, 2 times 2 is 4, 4 minus 1 is 3, and 5 cubed is just 125. Okay, so that's the approach we're using right there. Equate the bases, equate the exponents. So long as you can equate the bases, you should. Like, that's easier than doing a logarithm. So like, for instance, this next one, number 3, it says 4 to the 2x equals 1/2. Look at the number 4, look at the number 1/2. How do you rewrite both of those as the same base? What would the base be? 2. Because 4 is 2 squared, and 1/2 is 2 to the negative 1. So rewrite it. Keep the structure. So now 4 is really 2 squared, and 1/2 is really 2 to the negative 1. So now, again, your toolkit, when you raise an exponent to an exponent, remember all your rules. An exponent to an exponent means that you multiply the exponents. So on the left-hand side, we have 2 to the 4x. On the right-hand side, we have 2 to the negative 1. And since the bases are equal, the exponents must be equal. So 4x must be equal to negative 1. And so x must be equal to negative 1. Well, this next one's cool. Number 4. 2 to the power of x cubed minus x equals 1. Now, folks, sometimes I think authors do things like this just to mess with your head. They try to make something look as fancy as possible to intimidate you, to get you to quit. Go have a snack. Take a nap. Well, we don't have to go take a nap. So first of all, this is a base 2. How do I rewrite 1 as a base of 2? Get 2 to the 0. So I've got 2 to the x cubed minus x equals 2 to the 0. Now that does take some flexible thinking. You have to remember that the only way you can rewrite the number 1 is any base to the power of 0. Like, write it down once. 1 is equal to 2 to the 0. It's equal to 1 to the 0. It's equal to 3 to the 0. It's equal to 4 to the 0. It's equal to 5 to 0. It's equal to 8 to 0. It's equal to 17 to 0. I mean, my goodness. You can rewrite anything as a number to the power of 0, except, what's the only exception to that? 0 to the power of 0 is undefined. That's a fun bonus problem if you want to go home and think about it. Lose a little sleep. Okay, so now what? The bases are the same, so equate the exponents. X cubed minus x is equal to 0. Now what do we have to do here? Remember, we like to set things equal to 0 so we can use the 0 product rule. Something times something equals 0. What can I do? Yeah, factor the x out. So now I have x squared minus 1. I can continue factoring by the difference of squares. X squared minus 1 is difference of squares, toolkit. X squared minus a squared, yeah, x plus 1, x minus 1. And now by the zero product rule, something times something times something equals 0 only if x is 0, or x is 1, or x is negative 1. And whammo, apparently this thing has 3 answers. You can sit there and try them all out. You plug in 0, 0 minus 0 is 0, 2 to the power of 0 is 1. Plug in 1, 1 minus 1 is 0, 2 to the 0 is 1. And plug in negative 1, negative 1 cubed is negative 1, minus negative 1 is plus 1, negative 1 plus 1 is 0, 2 to the 0 is 1. So there were in fact 3 answers to that. Notice, this is not a polynomial. And yet, what was the highest power on x? 3, which implied that there were 3 solutions. Even though it's not a polynomial, but there was a polynomial inside of it. And so that polynomial had 3 solutions, which meant this thing had 3 solutions. Okay. Nice. Folks, how does everybody feel about this? All right. The very next one you can still do that way. I'm going to leave 5 for you to try. So let's move forward and try 6. Because 6, can you rewrite 3 and 5 as the same base? You cannot rewrite 3 and 5 as the same base. They're fundamentally incompatible. 5 is not a power of 3. Not a clean one anyway. So we have number 6. We have 3 to the 2x equals 5. What do we do? Remember, I've been saying a while now, if they give you the problem in exponential form, switch it to log form. If they give it to you in log form, switch it to exponential form. So they gave it to us in exponential form. So so we're going to switch it. So remember, this would be log base 3, keep the first number, and then switch. So it'd be log base 3 of 5 equals 2x. Then what? Yeah, do the change of base for log 5 divided by log 3. So log 5 divided by log 3. That's something you can type directly into your calculator. So now keep in mind that what you're about to do, you keep your calculator handy for the both next steps. Your calculator never leaves your hand. First you write log 5 divided by log 3. And your calculator has all infinite, well, it has all the decimals there. I'm just going to write down a couple. 1.464 ... equals 2x. And then what do we do to finish solving for x? Divide by 2. Your calculator still has all the decimals. So you shouldn't have cleared that out. Keep all those decimals, now divide by 2. Now we have the full answer. And you write down all of it. 0.7324867,604. Now how many decimals does more want? M-O-E-R.
Usually 3.
In my experience, usually 4. Yeah. So we want 4 decimals. So is the answer 0.7324? You would round up to 8, rounds up to 4. The answer that you would type into more is 0.7325.
If I don't use a computer, I usually go 5 decimal places.
Oh, really? Oh, well, hey. More uses 4. But yeah, different programs use different things. However, folks, I want you to take a look at something here. If you wanted to be wildly, nerdily accurate, okay, I want to solve for x. I could divide by 2, or I could multiply by 1/2, right? Because that's 2 over 1. So if I multiply both sides by 1/2, then that cancels, and we just have x. And over here, where does the 2 go? Yeah. The actual answer is log 5 over 2 log 3. That would be the exact answer. That would be the exact answer. If you want to type that in, you do parenthesis, log 5, divide by parenthesis 2 log 3. And that would be the exact answer. No rounding. That's the exact answer. By putting that 2 in the denominator where it belongs. All right. Well, number 6 was a really great example of a log problem. where we're solving an equation using logs. That's what we've been building towards. So number 7 is also a really nice example. You'll notice we're no longer trying to equate the base and equate the exponent. You can only do that if the base and the exponent are compatible. And if you look at number 7, 5 and 2 are not compatible. 5 and 2 cannot be rewritten as the same base. So your only choice is to do a logarithm. So for instance, in number 7, we have 5 negative x equals 2. So what do we do?
Log 5, 2 equals.
Yeah, so we've talked a lot about a lot of strategies in this unit. The fundamental strategy is if they give you exponential form, switch to log form. If they give you log form, switch to exponential. So we're going to rewrite this now as log base 5 of 2 equals negative x. This change base rule, log 2 over log 5, that equals negative x. Now who remembers, how do you get rid of a negative on x? You could, of course, divide by negative 1. You could also multiply by negative 1. That's a clever strategy. Because now our answer is simply x equals negative log 2 over log 5. And now that's the exact answer. No decimals necessary. You don't even have to type it into your calculator. That's just the answer. If you did want a decimal, by all means, you could get one. You'd get log 2 by log 5. And you'd get negative 0.43067. Or negative 0.407. And then you can even check your work. You could say, is 5 to the negative 0.4307 really equal to 2? So is 5 to the power of positive 0.4307? Yeah, I got 2.0075. All right. We've done some solid problems. The next thing we're going to look at is what if there are other numbers surrounding the exponential? So in that gray box that we read a second ago, they said isolate the exponential expression. Now, folks, do you remember that from the previous unit? When we had a problem like 2 root x minus 7 equals 3, how do we get rid of a square root? How do we cancel a square root? You square both sides. You can't just square both sides right now. You have to get rid of the 7, get rid of the 2. You have to isolate the root. And that's what we call it. You have to isolate the root before you can square the root. So same thing here. We need to isolate the exponential expression. The exponential is just e to the 0.1x. That's the exponential. So everybody write this like I do. You write down the problem. Say, okay, 2,000 e to 0.1x equals 4,000. And what I always do, this is just me. If you have a different strategy you want to use, that's fine. I box the exponential. It focuses my attention on what I want to isolate. I want to isolate the exponential. And so I just put a box on it because it helps me algebraically isolate it. Yeah, so I just divide off the 2,000, then I isolate it. 2,000. And that gives us e to the 0.1x, which is 2. So my exponential, is it isolated? It is. Okay, so now, to convert this to log form, that'd be log base e of 2 equals 0.1x. Now notice log base e, by definition, that's ln of 2. And then that's 0.1. Now right here, you could either divide off the 0.1, and you're done. So x is equal to natural log 2 divided by 0.1. You type that in your calculator, you get a decimal approximation. Natural log 2 divided by 0.1. I got 6.93. Or, everybody, I just want you to be flexible in your thinking. How could I rewrite 0.1? Instead of 0.1x, what fraction is 0.1? Yeah, it's a tenth. So instead of 0.1, I can write a tenth, and then how do I get rid of the tenth? multiply by 10. And I think that answer is even a little more elegant. 10 natural log 2. I think that's certainly nicer than natural log 2 divided by 0.1. And again, that's just flexible thinking. Or rewrite. I rewrote 0.1 as 1/10 and then multiplied by the reciprocal gave me a whole number, which is really nice. 10 natural log 2. Oh, that's a nice looking answer. Isn't it?
Yeah.
All right.
That's what I like to do.
Yeah. Cool. I seem to not have my numbers 9. Oh, I'm so sad. Well, let me get a copy. Here we go. Number 9. Is there a number 9? Oh, just go straight to 14? Well, hallelujah. All right. Folks, we're doing great. I realize we only have a few minutes left. We're a little tired. We're pushing through. Let's try these last 2 problems, I think, and that will be enough. So, number 14. Ooh la la. What makes this problem exciting? Greater than. Which, as soon as you see an inequality, what are we talking about? Yeah, above or below the x-axis. So we have 1,000, 1.005, and the 12x greater than or equal to 1,000. Okay? What do we do?
Or isolate the.
Yeah, we want to isolate the exponential. My exponential is right here. 1.005 to the 12x. So we divide by 1,000. And now that gives us 1.005 to 12x. It's greater than or equal to 3.
So that doesn't help.
Well, folks, let's think about what this looks like. I think it would be safe to go ahead and just log. But as soon as there's an inequality symbol, sometimes algebra doesn't work exactly the same way we expect it to. And it's actually better off thinking about what the graph looks like. So our question is 1.005 to the 12x, and we want to know when is that greater than 3? Right? So here's y equals 3. So everyone, you can just look at this now. When is this greater than 3? When is the purple graph greater than the horizontal line of 3? Yeah, everywhere to the right of 18.3, right? Okay, so now let's see if that jives with what we would get if we just proceeded with doing a log. So this is exponential form, so now let's do log form. Log base 1.005 of 3. See, this is very risky. I don't even feel comfortable using an inequality symbol anymore. I'm going to put a question mark here. Well, let's just say we proceeded from here. Now this one we can solve on our calculator, right? So that's going to be log 3 over log 1.005. So let's get the head answer. Log 3 divided by 1. That's 220. I'm just going to write down 2 decimals, but I still have all my decimals on the calculator, so it's fine. Now I divide by 12, right? And what do you know? It really is 18.3559. However, what broke down in the algebra? It produced the number we expected. We were looking for when is this thing greater than or equal to 3,000. Divided by the 1,000, convert it to log form, use the change of base rule, write it up to 12. What are they saying the answer is?
X, or go through greater than X.
X is,
Greater than.
they're saying X is less than 18. Well, that's not true. X is less than 18. Our curve is less than 3. We wanted it to be more than 3. So it's really important that we graphed this one to see that even though the algebraic logic did lead us to the number 18.3, the actual solution is anywhere X is greater than or equal to 18.351. Now, I don't want to make anybody feel uncomfortable or lose their faith in mathematics, because I don't have a concrete explanation for you as of right now. I mean, Lee, what do you think?
Trying to see if we actually did something wrong.
Is there a rule with like booking sign?
Well, I'll tell you one thing, folks.
Yeah, you know what it is?
What?
It's because when we divided by 12, wait, no, never mind. This was the thing, I was thinking of negative, but.
Yeah, but yeah, it's not.
Yeah, it's not that in there.
Yeah.
I don't know.
See, one thing you know for sure is that you can't just do x squared greater than 4 and then do square root of both sides. That's not true. Because if you square root both sides, that just tells you that x has to be greater than plus or minus 2, and that's the wrong answer. So there's something about doing algebra with inequalities that the algebra breaks down a little bit, and you need to look at the graph to support your answer. Right? So even though the algebra can show you the numbers, you need the graph to support your answer. So in this particular case, I'll think more about it, and we can talk about it next class. The answer is definitely x is greater than 18.3.
Yeah.
It's a really interesting question. The reason is,
Is
again,
it possible that when we switch into our logarithm, or when we're supposed to change our expression? Or
oh, like when you divide or multiply by a negative, you flip the symbol, and so when you switch to logs, you flip the symbol?
I'm just wondering.
Maybe. I mean, that's fascinating. I've never heard it. Okay, well, let's try one more, folks, because we had a couple minutes. So here's the last one.
Don't think I can think of.
Yeah. Now, folks, that said, you know, we've been looking at graphs throughout the entire class. You know, we've really emphasized that graphs are important. So let's look at this last problem and actually just graph it right off the bat. When is 70 plus 90 e to the power of negative 0.1x, when is that less than the straight line y equals 75? So when is it less than? To the right of 28.9. Okay. So we know for sure that's the answer. Like, if I'm going to stand up here and tell you to put your trust in someone or something, who should you always trust? The graph. The graph. Well, yeah. Yeah, the graph, your graphing calculator. Because that graph relationship is not going to lie to you. Whereas algebra breaks down certain times. You got to memorize certain rules about flipping symbols and whatnot. So let's try this problem again and see how it does. We have number 16, it's our last one. 70 plus 90 e to the negative 0.1x less than or equal to 75. I feel sad standing up here and not knowing exactly what to tell you about this. But I'm really excited because now I'm going to go home and read a whole bunch of articles online. And
Yeah, so on here it's saying x is greater than or equal to 18.33559.
Well, good.
I'm using Wolfram Alpha,
Now you don't
so
have to read it for you. Yeah, Wolfram Alpha agrees. Okay, so let's do this problem, folks. We want to isolate the exponential. So there's our e to the. We want to isolate it. Therefore, we have to subtract the 70. And then we have 90 e to the negative 0.1x. Less than or equal to 5. And then divide off the 90. And so that's e to the negative 0.1x less than or equal to 5/90ths, which is 1/18. Okay, so now we switch to log form. So that would be log base e of 1/18 equals negative 0.1x. And at this point, we put a question mark over that inequality symbol because I'm just not sure if that's going to be true. But this now is natural log of 1/18 equals question mark negative 0.1x. And the rest we do on our calculator, keeping all the decimals on the calculator. So natural log, parenthesis, 1 divided by 18, parenthesis, that's negative 2.89. Decimals are still in my calculator. Divide by negative 0.1, which is x equals all that divided by negative 0.1. The answer is, what do you know, 28.937. That's what we expected. Let's see if we kept the symbol. Oh, no. See, look at the last one when we divided by a negative. So you had to switch the symbol. And now that's saying x is less than the 28.9. But that's not what we said. We said we're looking for when x is greater than 28.9. So far, Lee threw out a pretty interesting conjecture that when you switch from exponential to log form, you might have to flip the symbol. That's an interesting conjecture. At this point, unverified, but maybe.
I'll look more into it.
Yeah, me too. That sounds really fun. If that is true, I want to know the proof.
Right?
All right. Well, in any case, folks, there we've done it. We've, again, solved some problems. Equations, that is, using logs. Okay, let's just see where we are, folks. When you come back, we're going to look at logarithmic equations and inequalities, and then we'll do some applications. Oh, well, let me just point out the way it works then. It's a great concept, and that way it's in your head. Thank you, Hector. I just want to plant the idea in your head.
Hey, better him telling us now than us having to figure it out.
No, it's better that you think about it. If you just get the idea in your head, you can think about it, you'll dream about it. Folks, remember, if I have 4 to the x equals 8, how do I solve a problem like that? I rewrite the base so that it's the same base, right? Because once you have the same base, the exponents must be equal. So the rule was equate the base, equate the exponent. Look at the very first problem. It says log base 10 of 3x minus 1 equals log base 10 of 4 minus x. This is the same situation, folks. The base or the log type is the same. So if you can equate the log type, then the argument must be equal. Since these are both log 10 on both sides, it must be the case that 3x minus 1 must equal 4 minus x. So you just drop the logs and you say 3x minus 1 must be equal to 4 minus x. And you move the x over, so that'd be 4x. You move the 1 over, that'd be 5. And then x equals 5/4. So you just do standard algebra from that point. But the key is, just like you can equate the bases and then equate the exponents, you equate the log type and then equate the arguments. And in that case, you just solve it the same way. Ooh, I can't wait to sit down and research inequality log problems.
Oh my gosh.